Good morning. I make it a couple of minutes past the hour, and so I think we've probably got enough people in the room to make a start on this Guideline Geo webinar. So thank you very much for joining us. And today we're going to be talking about the 100% duty cycle IP mode on the ABEM Terrameter LS2. For those of you who sat in these webinars before, there'll be a couple of slides that will be very familiar to you. For those who don't know me, my name's Jimmy Adcock. I'm the product manager for the ABEM line at Guideline Geo. I've been with Guideline Geo very nearly 6 years. I started as an applications engineer and then moved on to be the product manager last year. I've got a background in geophysics and worked before I joined Guideline for a survey company. If you don't know Guideline Geo that well, then I've just got two short slides just to give you a little bit of background about us. We are an instrument manufacturer. We have two brands within Guideline Geo. We have MALA, which is the ground penetrating radar line, and then we have ABEM, which are the more traditional geophysics equipment. So that's resistivity, seismic systems, and time domain EM systems. Guideline Geo itself, we're a company who's pretty well spread across the globe. This is kind of a summary of our main offices. These are a combination of technical and sales offices that are spread out across most of the time zones. I'm actually based in Manchester in the UK, but the real heart of the company is in Sweden. So our head offices are in Stockholm, our research and development are in Umeå, and our factory where we make all of the equipment is up in Malå. And Guideline Geo has actually been involved with geophysics since 1923, which is when ABEM was founded. So we've got quite a long history, and it means we've got a centenary coming up in about 18 months that we're very much looking forward to. Okay, so let's talk about what we're here for. That's this method of collecting IP data that can basically improve data quality and improve the efficiency in the field. Now, having a look at the list of participants, I know that we've got a good mix of people who've joined today. So what we thought we'd do is we'd start with just a little bit of theory about the basics of how resistivity measurements work and how we add induced polarization chargeability into those measurements, because then that helps us to understand the benefits that the 100% duty cycle measurement mode brings to survey. I would say that if you've got any questions as we go along, because I'm on my own today, what would be easiest for me is if you could add them into the Q&A section of the interface that you're using, the Zoom interface. Then when I get to the end, I'll go through that list of questions and I'll answer as many of them as I can. And then hopefully that will just help us kind of speed through the presentation part, and then we can get to the questions at the end. So basic theory, what are we doing? Well, all of the examples we're going to look at today are ERT, electrical resistivity tomography. So this is where we have a spread of electrodes attached to the instrument, and then we cycle through them using different combinations of electrodes to measure different areas within the ground beneath the electrode spread. And so by doing that, we can gradually build up a picture of the subsurface, either in 1D, 2D, or even 3 dimensions. When we collect the data, once we've flicked through the different electrode combinations and recorded the values, then on the screen, what we get is a pseudo section. This is the raw data. And so this is showing us depth against profile position. And then an apparent resistivity is represented by the color, with the higher values being red and the lower values being blue. At this stage, we call it apparent resistivity or apparent chargeability, depending upon whether we're looking at the resistivity or the IP data, because at this stage, all of those measurements, all of those values have been taken at the surface. And so the whole of the subsurface is contributing to the values that we record. So to get our final result, we then take that raw data off the instrument, we run it through some inversion software, that then tries to find a model of true resistivity or true chargeability that, if you repeated our survey over the top of it, would give you the same pseudo section. So it's trying to predict what the subsurface looked like based on the raw data we've given it and the raw data that it models within the software. And then once it's done that, it will give us a residual, and it will say, right, this model that I've presented you is this close to the raw data that you gave me. So if the model data is very close to our field data, our raw data, then we have a very low residual. And if they don't match very well, then we get a higher residual, and we might have less confidence in the result that we've got. So what's actually happening in the instrument when we do these resistivity and IP measurements? Well, with the resistivity measurement, we're injecting current, and that current is cycling from positive to negative to positive. So you can see here that this is time, the dotted line, and we'll say that's the 0 level. And so the measurement starts, the current switches on, and it starts flowing in the positive direction. And then this yellow phase is what we call a delay period, while what we wait for the voltage in the ground to build up and stabilize. Then the red period is where we actually measure the voltage to then calculate a resistivity loop. We then switch the current over, put it in a negative direction. Again, we wait for the voltage in the ground to stabilize, and then we take another measurement. And actually, we take 2 negative measurements during the resistivity sweep. Then we put it positive again at the very end, and we take another measurement of that voltage in the ground. So we've got 1, 2, 3, 4 voltage measurements that we can average out. We can then put that voltage into Ohm's law, which relates voltage, current, and resistance. And so we've got the voltage that we've measured in the ground, we've got the current that we injected into the ground, and that allows us to calculate the resistance for each of our data points. We then multiply that resistance by a volume factor, a K factor, which is based on the arrangement of the electrodes we've used, whether it's dipole-dipole, gradient, or a Venner or a Schlumberger, and that allows us to convert from that raw resistance into a raw apparent resistivity, and that's what we then take out to process. So with a normal resistivity measurement, switch the current on, take a voltage reading while it's flowing in the positive direction, switch the current over, take another couple of voltage readings, and then switch it back to positive and take a final one. Average them out, and that's one measurement cycle. And the reason we're going positive, negative, positive is that it avoids any drift in the measurement cycle. So if we just left the current on in one direction, and the charged particles that are what are transferring that current through the ground would gradually all drift towards one of the electrodes, and the voltage that we would see in the ground would gradually disappear. So we don't want to do that. We want to try and keep the ground in its original state. So if we go positive, negative, and back again, hopefully we can keep that balance of charge at 0 once we've finished. So once we have our resistivity data, well, then we can make our interpretation. And we either make an absolute interpretation based on what we know about the resistivities of different materials, or we can make a relative interpretation where we know that the inclusion of a particular material, whether it's water, mineral body, or some kind of pollution, will alter the resistivity from its natural values. So IP, it's a bit different. With IP, what we're doing is we're treating the ground like a battery. So we're putting the current on and we're letting the ground charge up. And then we're switching the current off, and we look at how the ground discharges over time. And there's a number of reasons why the ground might discharge more slowly. So basically, if we have no chargeability effect, no IP, then what happens is as soon as we switch the current off, the voltage that's in the ground just disappears immediately. If there's an IP effect, if we have a chargeable body or chargeable material beneath the instrument, then that voltage hangs around for a bit longer. So, more, it acts more like a battery. And so the reasons for this happening, there's lots of them, but it could be because of constriction between the fluid pore spaces, and primarily that current is flowing through the fluids that are in the ground. So if there are constrictions, there are tight spots, it's harder for the current to flow. It could be that there are charged particles in the ground, like clay. Clay, the individual clay particles carry a negative charge on them, and so they tend to hold on to those ions that are trying to transfer the current through the ground. So the presence of things like clay can cause chargeability. And then we might have a body that has a chargeability associated with it inherently. So it just has charged particles like mineral ores, for example. So all of these things can increase the chargeability. So how do we measure it? Well, the traditional way to measure IP looks a little bit like a stretched out resistivity measurement. So we still have current being switched on in a positive direction, and we still have a phase where the current is on in a negative direction to avoid this drifting effect. But in between the positives and the negatives, we have an off period. We have a time where there's no current flowing whatsoever. And that is when we're measuring the chargeability, the IP effect. In this period, we're looking at how the voltage in the ground decays over time. And so if we have big IP effect, high chargeability, this will be a very slow decay. And if there's no effect, then this voltage will pretty much plummet back down to zero straight away. So there's an issue here that doing an IP measurement takes quite a bit longer than just a normal resistivity measurement, because you have to have an equal amount of off time to your on time, because obviously you charge the ground up while the current's flowing, and you need to make sure that it fully discharges so that you can measure the whole of that IP effect before you then switch polarity and repeat the measurement. You'll see there's also this SP phase right at the end. So that's self-potential or spontaneous potential, and that is measuring the background voltage that's in the ground all the time. And that allows us just to double check that despite our positive negative switching, we still don't have any drift. So we can measure the voltage before we start, and then we can measure the voltage after the end of each measurement cycle and say, yeah, the voltage has actually started to drift one way or the other, and we can then correct for that. So if we're doing an IP measurement, this is now one complete cycle. So you can see in the resistivity, we had a positive, two negatives and a positive. And in this single IP measurement, we just had a single positive, then an off period, single negative, and then an off period. Why would we want to do IP? What are the advantages? Well, firstly, if you can collect IP, it's actually a really good secondary data set to help us interpret our resistivity, because this is that same resistivity table we looked at before. Find it in pretty much any geophysics textbook, where we've got lots of different materials and the resistivity values associated with them, or the range of resistivity values that are associated with them. And what we see is there's a lot of overlap. And so that makes it very difficult for us to make an absolute interpretation if there are similar materials present in the same environment. So for example, clay and fresh water have very, very similar ranges of resistivity values. And so it could be difficult to tell whether you've got a lens of clay or a perched aquifer. If, however, I was to add in the chargeability values, the IP effect, then we can see that actually that starts to separate out some of these materials by the scale of the response. So we said clay carries these charges on them, therefore it has a high chargeability, big IP effect. Well, that's very different from fresh water. And so therefore we can start to tell the difference between them. So just in this kind of absolute interpretation, there are benefits to be had from having that IP data set to help us differentiate between materials. But there are very specific uses of it as well, where the target that we're looking for responds well to the IP survey. And those might be, as we looked at there, hydrogeophysical method applications, where we're looking at the difference between clay, fresh water, looking at the difference between saline and fresh. It might be mineral prospection. This has traditionally been a big application area for IP, looking for large mineral bodies, particularly sulfide ores, where you get a very large chargeability effect associated with them. Increasingly, these last two are becoming important as well, and that is mapping former landfill sites. Quite often these historic landfill sites, big pits buried, a load of rubbish in it, but they weren't necessarily mapped particularly well. You know, the extents, lateral extents and depth perhaps weren't recorded in the early phases of the use of this site. And so now perhaps there's redevelopment or there's concerns about environmental problems. We can go back and survey them. And the fill of a landfill site tends to give you a very, very big IP effect. And then also contamination plumes, not just from landfill, but from other former industrial sites, quite often respond well to the IP survey method. And so it allows us to see these contaminant plumes that perhaps weren't so visible before. And actually this photo on the right-hand side was from one such survey where we were working alongside a landfill, former landfill site, and we were looking for the leachate. We were looking to see if anything was leaking out of that particular landfill. And I'll be brutally honest, this is one of those occasions where perhaps the geophysics wasn't entirely necessary, because as we progressed along our survey line, we got to an area where most of the trees had died. So that was probably a giveaway as to, yeah, there is some leachate here. And if you actually look at the overhead photos of the site, that's the covered landfill. There's a forest around it, and there's this ominous area of no trees right next door. But more than that, by doing geophysics over sites like this, we can actually look at how bad that plume is. You know, how deep does it extend? Is it likely to get into the bedrock where perhaps there might be aquifers that surrounding communities are using? So the geophysics does bring extra benefits on this kind of site. So let's look at a couple of examples of where IP have been used, and then we'll move on to the 100% duty cycle. So anyone who's sat in on one of our resistivity webinars or introductory sessions before will recognize this data set. So this is an example, again, from a landfill site, and we've got the chargeability data on this profile, and we've got the resistivity data on the bottom right. And the problem they had here was that the local community who extract their water from the bedrock were finding that there were increasing levels of chemicals in that water, which originally had been quite fresh. And so the understanding was, well, there's a landfill site nearby, we think that something is leaking out of that. Now, they didn't know exactly how big the landfill was, they didn't know exactly where it extended or how deep it was. So it wasn't a case of just being able to dig in on one side and start to put in some kind of geotextile to protect the bedrock. They actually had to do the survey first. And so what you can see from the chargeability is that we get a very clear indication of the extent of the pit itself. So that waste material that's in there, there's lots of metals, organic materials, salts, alkalis, acids. It's one big battery. So you get this really big IP effect. That waste in there holds onto the voltage, holds that charge for a long time. And so we get these red values, these high chargeability values that delimit the pit very, very clearly. But it wasn't obvious from the IP where the bedrock was or how anything leaking out of here could be getting into the aquifer. And actually the resistivity data set allowed them to see that. So where there wasn't a big contrast between the overburden and the bedrock in the chargeability, the resistivity values were very different. And they could see that there was a sudden break in the bedrock. And so that was interpreted as some kind of fracture or fault. And so you've got leachate, which is lower resistivity, fluid that's coming out, lower resistivity, over and into that fault and percolating down and into the aquifer. So using the two data sets together, they were able to get all the information they needed. As we said, there's another big application area for IP is mineral prospection. And everyone loves the idea of finding gold. So here's an example of gold deposits. On the top, we have the resistivity survey, and on the bottom, we have the chargeability data, again, collected at the same time. And what you can see from the resistivity is that it's generally very highly resistive bedrock here, but there are regions where the resistivity drops off. However, from that resistivity value alone, you wouldn't know necessarily whether that is because of some kind of mineral inclusion, a mineral vein, or there are fractures in the bedrock where groundwater is residing, and that groundwater is then reducing the resistivity. If we look at the IP effect, though, if we look at the chargeability, we can see that there are some very clear, let's call them hotspots, where the chargeability is very high, and we wouldn't expect that from water. So we can suggest that, yep, that's probably the area where we've got some kind of mineral inclusion. And if you were to collect a series of parallel profiles, then you could look at how that seam moves through the landscape, and you could find a location where that seam is closest to the surface, so that you could then drill and test to see what the yield would be. And then the final one is kind of hazard mapping, more environmental type measurements. And this is looking at quick clay. So clay in general, if you're constructing on a site, can be problematic because the clay can act as a slip plane, you know, where the material above, when it's loaded and heavy, could actually slide across the clay. In Scandinavia, they have this specific type of clay called quick clay. It's a marine clay. It has a lot of salt in it. And when it has the salt in it, the salt gives structure and strength to the clay. But over time, the salt gradually washes out, and then that weakens the clay, and even just the smallest disturbance can then cause that clay to liquefy, and everything on top of it then moves. And there have been a couple of cases in the last year that we've, like in Norway, for example, where this has been the case, and whole hillsides have just shifted in one go. And so what you're looking for here is the difference between where the clay still has salt in it and where the clay does not. So salt clay has incredibly low resistivity, and clay without has a slightly higher resistivity. So we can map those regions, but then we can also look at the IP to ensure that what we're looking at really is clay and not some kind of groundwater deposit, for example. So they were interested in where is the clay losing its salt? So those are the green regions. And the problem with those values, those green values, is that they're similar to groundwater. So add chargeability data in, and you've got a more confident interpretation. Okay, so let's move on now to what we're here for, the 100% duty cycle. So what is this? What is this method of collecting IP data? Well, first of all, let's explain what duty cycle means. It's a way to describe how active the transmitter is. How long is the current switched on for compared to how long the current is switched off for? So in a traditional IP measurement, we would call it a 50% duty cycle, because we had the current on for, let's say, 1 second, then we switch it off for 1 second whilst we measure the IP effect. Then we put it on in the opposite direction, in the opposite polarity for 1 second, and then we switch it off again for 1 second. So 50% of the time the current is on, 50% of the time the current is off. So in a 100% duty cycle measurement, current is always on. There is no off time. So we go from the positive polarity and we switch immediately to the negative polarity. And that's where we're going to extract the IP effect from. Now, this method was developed by researchers at Lund University and Aarhus University working in partnership. So they did all the clever research and testing of this. And then Guideline Geo have commercialized it and put it into a resistivity system, into a marketable instrument. So this 100% duty cycle mode, this is an advanced feature. This is on the advanced models of our Terrameter LS2. So if you've looked at the tech specs, if you know our instruments, then you'll know that we have a range of models from basic through standard up to advanced. And so it's the advanced ones that have this capability. Now, if you happen to be an existing user and you have a basic or a standard Terrameter LS2, don't forget that if you want to enable this 100% duty cycle mode, you don't have to send the instrument back to us. So the LS2 has hardware licensing, which means that the specification is controlled by a license code. And so that means that if you are using a basic or a standard and you want to upgrade, then you can contact our sales department. They'll tell you what the cost for the upgrade is. And as soon as that's paid for, we'll provide you with a fresh code, and then you will have the full capabilities on the instrument. So what happens? What's the reality of these 100% duty cycle measurements? Well, let's start by reminding ourselves what traditional IP waveform looks like. So we take a background reading of the voltage in the ground as our starting point. We then switch the current on, and we have a delay time. And that is while we wait for the voltage to stabilize in the ground. Then we have a measurement period, and that's where we're recording the resistivity values. Then we switch the current off for 1 second, and that is whilst we take our IP measurement. Then we repeat the current injection, but in the opposite polarity. We have a delay period while we wait again for the voltage to stabilize in the ground. Then we take our resistivity measurement, and then we have our final IP measurement, now looking at the negative decay. And then a final background voltage reading, just to be able to remove any residual drift that has happened during that measurement cycle. And so that's for a 1 second IP measurement. And you can define how long you switch the current on for. So it could be 1 second, 2 seconds, 4 seconds. And the longer you have the current on for, obviously the more you'll charge the ground up. So if there is something that has a very high chargeability associated with it, you would want the current on for longer to make sure that you fully charge it before you then switch the current off to then measure the discharge. So if you look at a 1 second measurement, you've got 1, 2, 3, 4 seconds in there just for the measurement of resistivity and IP, plus you've got an SP measurement at the end. And if you think that that's one stack, that's one measurement cycle, and you might want to repeat those to improve your signal to noise ratio, and then you've got hundreds of current injections to do to complete a measurement, then you can see that IP is quite a slow procedure compared to a regular resistivity measurement. So let's get rid of that and let's look at the 100% duty cycle method. So in this one, we take a background reading of the voltage, and then we switch the current on like we did before for 1 second. We have a slightly longer delay time now, slightly shorter resistivity measurement time, but we can actually play around with those ourselves. And then we switch the current directly from positive to negative. And then we switch directly from negative to positive. And what are we doing? Well, we're looking at this curve here. So when we had our, if we look back at our resistivity measurements, we look at how that was defined. If you remember, we had a delay in there to allow the voltage in the ground to stabilize. Well, why isn't the voltage in the ground stable? Well, the reason it's not stable is because we have an IP effect. The ground is charging up over time. So we need to take that into account. And there's no reason, therefore, why we can't extract the IP, the chargeability, from that switch over time. And that's what the researchers at Lund and Aarhus were working on. So we switch over, we use that delay period to measure the curve, and then we can also take our resistivity value. And then we switch back and we do the same again. We measure the IP effect in that delay period, and then we take another resistivity measurement. So this is a much shorter cycle now. And not only that, but we're not measuring just from positive to negative, positive to 0, and then negative to 0. We're actually measuring from positive all the way through to negative. So we have a much bigger curve to integrate, basically, a much bigger effect for us to record. And in IP, they are traditionally very small values because you don't have current flowing when you're taking the IP measurement. You've switched the current off in the traditional method, and so the voltage is always getting smaller and smaller and smaller. And so that means that it can be very difficult to separate out what is an IP effect from background noise. So by effectively making it more active, like having it during that current switchover, we're increasing the scale of the effect, making it easier for us to map it over and above any background noise there is. So first of all, we've got a bigger response. We've got quicker measurement, but it's not just about the speed of it. If we compare the two different types of measurement, so here's the 50% duty cycle, current on, current off, current on, opposite polarity, current off, and then repeat. If we look at this for a 2-second measurement over a time of 16 seconds, for the traditional method, we get 4 measurement positions. We get positive to 0, negative to 0, positive to 0, negative to 0. So we've got 4 IP that we can then average to give us our final result. If we use the 100% duty cycle and measure over the same 16 seconds, well, now we've got 7 opportunities to measure that IP effect. So there are 7 switchovers in here. And we're not just measuring, as I say, from positive to 0, we're measuring all the way through. So everything about this is helping us to improve that all-important signal-to-noise ratio. It's important when you do a resistivity survey, but it's critical when you do IP because the scale of the signals are traditionally so much smaller. So let's just have a quick look on the instrument, what this, how we would set this up. Is it particularly difficult? So I don't know if you can see it behind me. I have a Terrameter LS plugged in, and I've connected to it via its onboard Wi-Fi. And on the Terrameter, there is like a Vnc server. So Vnc is a remote operation protocol that kind of IT departments use to control your computer if you've got a problem. So we have one of those built into the LS, so you can actually screen mirror and control with any device you want, because VNC communication apps are available for Android, Apple, PC, Mac, Linux, you name it, you can get a VNC viewer on it. So I'm actually looking at the instrument here. This is live, so I can control the instrument. So let's just look at how a measurement would be set up. So I'll just create a new project. And then create a new measurement. So that's just setting up a measurement script, a measurement protocol. And then it automatically takes us then into the settings pages. And so what we need to do to set up a 100% duty cycle is just to tell the instrument that that's the type of measurement we want to take. So you can see here at the moment, it's set up for res and IP. So that is the traditional 50% duty cycle. So then I have an option to just do a measurement with just resistivity data, an option just to measure SP, so no current injection whatsoever, or to run this protocol as the IP 100%. Now that means it's also going to be collecting the resistivity data at the same time. Now, fortunately, I don't need to remember what the settings are, what good settings are for this. I can actually just load some in. So we have preloaded settings on the instrument. So I could say that I want to do 100% duty cycle 2-second measurement. Yeah. And so now that will have updated all the necessary inputs on here for delay time, acquisition time, and how many measurement windows we have. So when we're measuring IP, we don't just measure a single value instantaneously. We're measuring that curve over a series of time windows, basically integrating the voltage under the curve. So that allows us to measure much more precisely these very small changes that are associated with the IP effect. So if I go along, it's also set up some good kind of starting settings for the transmitter, and then also, as I say, the individual time windows that it's going to split this curve into to record the effect on. So it's dead simple. It's exactly the same as you would set up just a regular IP measurement. And if you don't want to use your own settings, then there are plenty of options in there to load them in. So then we could jump from there to our measurement screen, create a new station, and then we'd be ready to start measuring. Although obviously I can't measure with this because it's sat on a box on a sofa. So we'll leave that there for now. So what I'll do is I'll look at some real data that's come in from an instrument. And this is actually just, I thought I'd use some recent data rather than something from the archive. So this data was actually collected on Tuesday of this week. So some of my colleagues were out doing a bit of training, and they were doing some measurements in the US in this particular landscape. And they got some really weird IP effects, a really big IP effect that you wouldn't really expect from the geology that they were working over. And if you bring up Google Earth for the region that they were working in, and then sort of scroll back a couple of images on the date line that you get in Google Earth, you can see that they are actually measuring over this massive scar. And that scar is where a really big water main has been put in, a big pipeline. And when I say a big pipeline, I mean like really big. So these are the pipe sections that have gone in, that have been buried along the line of that scar. And so if you need any idea of scale, that's a big US house, that's a car. I dare say you could almost drive a car through these pipes. So there is something pretty big under the survey line. So let's have a look at that raw data. And I'm actually going to look at it in LS Toolbox, which is our companion software that comes with the LS Toolbox. So this is free software. And we use this for downloading data. We use this for filtering data before we take it forward for inversion. So we can use it for kind of quality analysis. And we can also use this for sort of updating software and stuff on the instrument. So I've removed the positional information just so that the landowner doesn't, feel aggrieved that we've shown data from their site. So what we've got here is the summary of the measurement. So it tells us all about how the instrument was set up. And down at the bottom here, we can see that we've got the measurement settings. So at the moment, what I'm looking at is task number 5, which is dipole-dipole. And we can see that task number 5 was using the resistivity and IP50 mode. And we can then see that task number 6, which was also a dipole-dipole, task number 6 over here, that was resistivity and IP100. So let's have a look at the full, what we call the full waveform. So the Terrameter LS doesn't just record like an averaged value for the output current and the measured voltage and apparent resistivity. It can actually record everything that the instrument is doing during a measurement cycle. So up to 9,000 times a second, you can record how the output voltage and the output current change. And then you can record how the input voltages change over time. So let's look at task 5. This is our 50% duty cycle. So let's have a look at the full waveform. The black line is the current, and the LS is a constant current instrument. That means that you have fixed current once it starts injecting. And then the brown orange type line is the voltage that's being used to drive that current into the ground. And so we can see that, sure enough, this is a traditional resistivity type measurement, traditional IP type measurement, where we have background SP reading. We then have the current switched on in one direction. The voltage varies just to keep that current constant throughout the cycle. We then switch the current off, and then we measure IP during that off period. Then the current goes on in the opposite polarity and then switches off, and then we'll take an IP measurement in there. So let's now jump to task 6. So this is our 100% duty cycle, and look at the waveform there. And so now this is what we expected to see. We've got our background voltage measurement, but then the current is on, then it switches polarity immediately, then the current switches back and there's no off period. And if we look at the voltage coming in on one of the measurement channels, so we can see here that we've got background measurement, we've got a bit of background voltage around. Not entirely surprising, this was an urban environment, so there's bound to be a bit of spurious voltage in the ground, there's bound to be a bit of noise in there. Then we see the current switches on, the voltage in the ground builds up to a plateau. Then as the current switches over, the voltage in the ground changes polarity, and then we see our IP effect. And so that is what we are extracting. That's where we're getting this chargeability information from. Then we switch back again, and then we switch back again. So in there, we're taking 1, 2, 3 IP measurements from positive all the way through to negative, then from negative all the way through to positive, and then from positive back through to negative. So it does exactly really what I put in those schematics. So let's have a look at the raw data. Let's have a look at the raw pseudo sections for the chargeability. So this is task 5. So dipole 1, and task 5 was our IP50 method. And so here's the chargeability values for the first time window. And then if I jump to the next pseudo section, these are the chargeability values for the first time window with the 100% duty cycle. So you can see that we've pretty much got the same effect, the same response, except in the 100% duty cycle, we've lost a few bits here, and I would be pretty sure that these data points are noise. They're just isolated points. We wouldn't really expect to see that. So these are probably noise we're not getting in the 100% duty cycle, because we've been able to improve the signal to noise ratio, been able to stack more often. So that's the theory of it. I did some a few bits of stats on this as well, because I can, if I open the table of values, these are the average values. This is everything the instrument has recorded. And in here, it will tell me how many cycles the instrument has done. So how many repetitions it's taken for each of these data points. And so I can compare how many times the instrument repeated the measurement for the 100% duty cycle and also for the 50% duty cycle. And so that will be recorded in this table. So number of cycles in there. And then also in the summary, this is going to tell me how long the measurement took. So you can see I've got a date and time stamp on here for measuring started, and then another timestamp when the measuring was finished for 50% and the 100%. So I've taken all of that information and put it back into the presentation. So if we look at the 50% duty cycle, that particular profile that they collected took 86 minutes. And because in a 50% measurement, the instrument decides whether to stack or not based on the quality of the resistivity result, not the IP result, then that means that 70% of the data was saved having only done one cycle. So the resistivity data was great, but it limited the number of times we could stack the IP. So for 70% of the data points, we had one positive decay and one negative decay because there was just one measurement cycle. For the other 30% of the data, the instrument had to stack twice to get the resistivity data to an acceptable error limit. So that means that for those other 30%, we had 2 positive decays and 2 negatives during those 86 minutes. So, I mean, that's okay. You get a decent enough data set out of that. But let's have a look at what the 100% duty cycle did for us. Well, by using that mode, using exactly the same setup, nothing was changed. We just said we want to collect 100% duty cycle instead of 50. Then it took us 54 minutes. So we're talking about a significant time saving in the field for this particular profile. But more than that, that was actually doing what we call 4 pulses, 4 current pulses for every data point. And if we have 4 current pulses, 1, 2, 3, 4, so positive, negative, that gives us 3 switchovers. So already we've got an extra stack compared to our 50% duty cycle, but those are also positive all the way through to negative. So each measurement is a bigger effect. So again, helping us to improve the quality of those measurements that we recorded. And then just to prove that it kind of all comes out in the wash as well and everything works at the end, I just quickly took that data out and ran it through Res2D and ran the inversions. And so these are the final models for the 50% duty cycle and the 100% duty cycle. So we can see there's a slight difference in the absolute scale of the IP effect, but in terms of the interpretation, in terms of determining where that feature is, it is incredibly similar between the 2 different methods of data collection. Okay, so that's a kind of brief introduction to what the 100% duty cycle is and what it can do for you. I haven't taken this particularly deep in terms of theory, and so I'm sure there's plenty of people out there who would like to know a bit more about this. So there's some further reading here that you can go and look up. And if you want a fairly easy but slightly more technical level of introduction to the method, then we have a white paper on our website that you can download. So if you go to our resource center, filter by LS toolbox, Terrameter LS2 by the instrument type, and then look for white papers, you'll be able to find that document. And if you want to go back and look at some of the original research, some of the journal articles that were surrounding that, then you can find those. They're all open access via the Lund University web pages or the Aarhus University web pages. So yeah, they're all there and easy to access and read. So let me have a quick look at the questions that came in whilst I was talking. One question, I'd like to see you demonstrate how to carry out 3D field setup. I've tried with LS2, but I'm not getting a good result. And so that will depend basically on what equipment you have, how many electrodes you have, and then how good the protocol, the measurement script that you got are using. So usually to do true 3D, you need a lot of electrodes because you want to cover a decent amount of ground and get a decent depth penetration. You need a lot of electrodes. So if you've only got a small spread, doing true 3D isn't always particularly easy. And then it's worth looking at how your protocol is running. And so again, designing the protocols so that you have a good balance between the number of data points. With a 3D data set, it's very easy to collect a huge number of data and take an incredibly long time. But things like pole dipole, they're good methods to use because they can give you extra depth. But normally when people want to do 3D, we would recommend 2.5D, which is where you take a series of 2D profiles and combine them into a single 3D block afterwards. So Phillips, I would suggest please contact me via support@GuidelineGeo. I can give you some tips on how to improve your data quality. I can also show you our spread and protocol software that allows you to generate your own 3D layouts and measurement scripts. What else have we got? Can this, oh yeah, a few people have asked this. Can this method be used on a Terrameter LS1 on the original version? No, unfortunately not. The user interface is different on the LS2 in terms of what happens behind the scenes, and there were some hardware changes between the two instruments. So this is only possible on a Terrameter LS2. Can we, Renee has asked, can we use Res2D to invert 100% IP? Yes, you can. So I probably should have made that clearer. When we collect this data, what comes out at the end is absolutely no different. If I open up my LS toolbox again, if we look at the table of values, sorry, there we go. So this is the 50% one. This is task 2. So that was a gradient with a 50% duty cycle. And this is task, sorry, that's with 100% duty cycle. Task 3 was gradient with 50%. The output is exactly the same. So you end up with these millivolt per volt values for each of the measurement windows. So effectively what comes out at the end of the measurement is exactly the same as what would come out after a 50% duty cycle. So you have still got the same format Res2D file that you can then import and process. So there's nothing different about what we do after we take the data off the instrument. Everything is happening on there. The only thing that you can benefit from is that you could use Aarhus Workbench, which does a different type of inversion. That does an inversion which actually looks at the individual time windows rather than just look at it as a single chargeability value per data position, per data location. Looks at the shape of the curve, and that allows you to extract other parameters from that IP data, such as tau and C, as well as the chargeability value. Can we use the SP measurement to QC the IP data? You probably could. You could also use the full waveform and actually look at the shape of the decay curves. So if you are intending to use Res2D to do the inversion, then doing the processing in Toolbox and looking at the decay curves in there will help you decide whether or not the decays are good or bad. If you are using Aarhus Workbench, which is the other software package that we would recommend for doing resistivity and IP inversions, they actually have tools in there that can allow you, again, to filter through and QA the individual IP data points and even individual time windows. How to perform ERT on rocky strata? It's very difficult. The hard work method is to drill holes into the rock, fill them with some kind of bentonite clay, something like that, something very conductive, and then push your electrodes into that. The alternative method is to actually use plate electrodes, so big flat electrodes. You put a good layer of bentonite clay underneath them, and that gives you a big surface area on top of the bedrock. So that's probably the easiest method. What is the purpose of IP windows? Do I need to process it in separate windows? Kind of covered that just now, and I somehow managed to answer a question before I'd read it. So no, if you're taking the data out of LS Toolbox and say putting it into Res2D, you can sum all of those windows into a single chargeability value. If you're taking it into the Aarhus Workbench software, you can then actually process it using what's called a cold-coal inversion, which will then look at the shape of the curve and give you these additional parameters. So it's entirely up to you, depending upon the software that you intend to use. Can I share my contact details? That's a really good idea. Let's move on to the last slide. There's my email address at the bottom. So take a note of that. And how to determine the proper setup for delay time and acquisition time. Simplest method is just to use those preloaded settings on the LS2. So there are a bunch of preloaded settings for just regular resistivity measurements, for traditional IP measurements, and the 100% duty cycle measurements. And they're really good, like what I call starting settings. So settings that will work in probably 90% of survey locations. If you want to change those values, then what you would normally say is that if you think there's a big IP effect, then you would extend the delay time, because if you're doing a traditional resistivity measurement or IP measurement, before you start taking the resistivity value, you want to make sure that the voltage in the ground is stabilized. So lengthen the delay time. If you're in a very noisy environment, then you want to extend the acquisition time, because you want to be able to average that resistivity value over a longer period. Always better to collect for too long than too short. That's the simple thing. So if in doubt, lengthen it, provided you've got the power to be able to run the instrument for a longer period of time. But if you measure for too short a time, then either you're measuring the voltage whilst the ground is still charging up, or you're not averaging for long enough, and therefore the chances of the data being influenced by noise that's in the ground around us from all sorts of sources is much higher. How do IP measurements compare in single channel and multi-channel mode? Is the data quality much different? Does the IP values change with the measuring time? Okay, so single channel to multi-channel, there isn't a huge difference if you're working relatively shallow. If you're on quite a deep site, then what we said was that the data sets, the signal, the IP signal, is much smaller than the voltages that we record for resistivity. So if you've got a particularly deep survey, then as you get deeper, the signal strength gets weaker all the time, whether it's resistivity or IP. And Venner and Schlumberger, the single channel measurement protocols, electrode arrangements, they have inherently much better signal to noise ratio anyway. So for a given current input, you get a bigger voltage output from the ground. So there are advantages to using them because you increase the signal strength. And then you need to really just determine whether the increase in field time is worth the increase in data quality. So, it's usually a bit of trial and error, and see whether doing that has benefited you enough to warrant the fact that you'll be in the field for 3 or 4 times longer, maybe 6 or 8 times longer, depending upon how many measurement channels your instrument has. Do the IP values change with the measuring time? They do, actually. There's a paper on that as well. Another one from, I can't remember whether it was Lund or Aarhus or both, looking at the effect of the current on time on the chargeability that you get. So in terms of relative result, you still get the same thing. You still see that there is an increase in chargeability around a particular body. If you have the current on time longer, actually that chargeability effect quite often appears to be much bigger. So absolute terms, the model that you get out will suggest a higher chargeability if you use a longer acquisition period. And most of the inversion software at the moment, like for example Res2D, won't take into account that current on time. But in terms of relative, saying yes, there is something there, you'd still get the same kind of interpretation out. Other questions. How do you reduce crossfeed effect when the cable may not be perfect in insulation? From Renee. So this is the issue of getting a bit of crosstalk between the multi-core cables. So your spread cables, you've got all these cores inside, they're all very close to each other. So there's a possibility that you can get some induced voltages from one to another. And what some people do, if it's a serious effect, if it's a big enough effect to be impacting your data, and quite often it doesn't change your interpretation. The bit of noise that you might end up with doesn't change your interpretation. But if it is, what you can do is you can separate out your transmitting and receiving electrodes. So you could have a spread where current is injected on one cable, and then the voltage is measured on another cable. Generally, the signals that are coming back are so small that you don't have such this kind of crosstalk effect. In the Terrameter LS, it's also minimized by the fact that all of our measurement channels are completely isolated. So once you get into the instrument, you don't have any fears of cross-contamination between measurements, because every channel is completely isolated and on its own digitizer. Does the LS2 increase depth penetration, especially in dry areas for minerals like copper, etc.? The LS2 Advanced has the same output power as the original LS. However, if you're talking about IP, the fact that you can now use the 100% duty cycle means that you've got better signal to noise ratio, and therefore your DOI, your depth of investigation on an IP survey, will be better with that alternative method. If we were to use 100% IP for 3 lines, test it out, gather the other 5 lines with the original res IP, pseudo sections from the 2 modes be comparable, then similarly gathered 5 lines in res mode and then 3 tests in res IP mode with pseudo sections be comparable. Okay, the res bit would be pretty much identical between all of those, whether you're using res and IP, i.e. the traditional method, or 100% duty cycle, they would all be exactly the same. The IP pseudo sections would be very similar, but you might see that there is less noise. So like those examples that I showed in LS Toolbox, pseudo sections, you can see that there's a little bit of difference, and primarily we're talking about, oh, accidentally stopped sharing there. Let's share that again. We're talking about differences in noise there. So yeah, that's basically it. If I sum all of the IP values, so instead of just looking at a single time window, again, we can see that if you average it over all of the windows, again, they look very, very similar. Although the later windows probably you wouldn't take the values from, you'd probably filter some of those data points out. But this is everything, the good, the bad, and the ugly in there. So that's unfiltered data. Let's see. Right, that's all the questions in that box. There was one other. Let's have a look at the comments. Can you assess? Oh, I've done that one. That was in the Q&A. Forward the links for further reading to the chat box. I could do that. That's a very good idea. Yep. Let me do that now. And we'll also send out, there'll be a copy, a recording of this presentation that we will share with you. So where's the chat box? First one, I won't follow the link, you'll be able to find out what the title of each of the papers are. That one, and then, so these are the 3 kind of, scientific papers, journal articles, and then the final link is going to be to our white paper. So copy link. Paste. There you go. Those are all of those. Let's have a look if there are any other questions that I've missed in here. Does IP survey require non-polarizable electrodes? If so, what difference will it make to normal steel electrodes? If you're using a Terrameter LS or an LS2, you can get away with using the stainless steel electrodes, provided you're not looking for really, really fine, small IP effects. If you're looking for something terribly subtle, then yes, I would recommend that you have a protocol that's written so that you have the voltage recorded on your NP electrodes, your non-polarizing electrodes, and current injected on stainless steel. However, you can quite happily use stainless steel especially if you're looking at relatively large IP effects. And there is a paper, which I won't be able to lay my hands on the link to directly now, but by Torleif Dahlen, who is one of the authors on the links that I've just shared at Lund University, and they did a comparison of stainless steel electrodes on a Terrameter LS1 against non-polarizing electrodes. And the conclusion was, yes, you're always going to get slightly better data quality if you use non-polarizing electrodes, but ultimately the compromises that you might have to make in terms of your field work, especially if you're on time pressure, you know, if you're a commercial surveyor as opposed to a researcher, the compromises that you have to make maybe aren't worth the improvement in data quality. Okay, I think I've covered all of the questions. That was really good. I think that's the most questions I've ever had at the end of a webinar. So they always make me happy because that means people have been paying attention because they've got questions to ask. So thank you very much for attending today. I've enjoyed this one. Hope you have too. Oh. And as I say, we will send out a link to the recording. It will be up on our Guideline Geo YouTube page. So if you want to watch it again, you can find it there. Or if you have any colleagues who missed this, you can direct them to that. And as I said, if there are any questions, either contact support@guidelinegeo.com or my email address is at the bottom there. So thanks once again for joining us, and I hope to see you at another one of these webinars very soon.